Hello everyone, welcome to ExamRat. So our topic for today will be resistance, and we'll learn about parallel resistance and series resistance and discuss some of the sums. So in our last class, we had talked about Ohm's law, right, where we saw that V equals to IR, where V is the potential difference, I is the current through the particular metallic wire whose potential difference between the 2 points is V, and R is the resistance offered by the metallic wire to the flow of the current. Okay. So today we're going to be talking about how this resistance can be input in a circuit in two ways. One is a parallel pattern, a series pattern, and another one is a parallel pattern. So we have to understand the difference between two. So you can understand that in series, what you are seeing is that there is the resistance are connected to each other one after the other, right? So if you think about it, in our last class when we talked about potential difference, it was between any 2 points, like if this is A and B. So the potential difference between this can be VA minus VB, considering that A is at a higher potential. Next, again, if we take a C and D wire, then the potential difference between this will be VC minus VD, and the potential difference between these 2 points will be VB minus VC. Okay, so what you can understand from here is that the potential difference between any 2 points will be the same unless something is connected to it. For example, if I say that, suppose this here is a resistance, and this is a bulb, and then this is a battery. Okay, so the thing is that here, whenever you insert something into the circuit, the potential difference between those 2 points is different than what it would have been if there was nothing here. So what I mean by this is that if you consider any arbitrary 2 points here, M and N, so Vm minus Vn, and let this be C and D, is not equals to Vc minus Vd. Okay, because the difference is that here you are connecting a resistance. Now the resistance will pass some current through it, like a lesser current rather, through this than it would have been if it passed through this point, right? So whenever you're changing the current, like you're increasing it or decreasing it, automatically the potential difference between those 2 points will decrease or increase, right? So in the same way here also, if you've connected the bulb, then the potential difference between these 2 points will also become unique, right? So from this, what I mean to say is that here, if you notice that all these resistance, like the point of potential difference between each of these points, V4, V3, V2 and V1, you can understand how they are all different, right? Because we know, for now we know that all these resistances have different values, right? Because R1, R2, R3, R4, it can be so that in some cases it has the same resistance, but here we're talking about all of them having different resistance. So in that case, you can understand that all of their potential differences will be unique, right? Will depend on the value of the resistance here and the amount of current flowing through each resistor wire. Okay. So what you can understand from here is that the sum of the potential difference between all these points is equivalent to the potential difference of the whole circuit. Means if I draw a circuit like this, then you can understand how, if I told you that the potential, the electric potential of this whole circuit is V, then you can very well understand how V is equals to V1 plus V2 plus V3 plus V4, right? Because this will complete the whole circuit. So when we're talking about series resistance, what do we have to understand is that the sum of the potential difference between each resistance is equal to the potential difference of whole circuit. Right? Okay. So, this we've understood how the potential difference is going to be different each time we connect something. Okay. Now, since this battery is providing say 1 ampere of current, you have to know that all like the current flowing through all these resistances will be equal to 1 ampere. Like the magnitude of the current will not change. Why? Because I told you that when we talked about how the potential difference was different, it was basically the maneuver of the resistance that was basically determining the potential difference. Okay. And accordingly, the flow of the current would have been altered, but it does not mean that the value of the or the magnitude of the current flowing will decrease. Okay. So if I tell you that this circuit will give you 1 ampere of current, then you have to assume that all these resistance, like the current flowing through all these resistance, will be 1 ampere. Okay. So 1 ampere will move through here, 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 and here. Okay. So we know that current remains same. So now, since we have understood the two main points, that is potential difference is the sum and current remains the same, now I think we can calculate what can be the series resistance of a single circuit. So taking the previous example, if this is Rs, so I into Rs equals to Vs or V of the whole circuit. Let's just write it as V. So we know that V is the sum of the potential difference of all the individual resistances, right? So we can write it as IR1 plus IR2 plus IR3. Okay. So here if we take I common, this will be R1 plus R2 plus R3. So you can see here that the I is getting striked off. So for a series resistance, the total resistance will always be the sum of the individual resistances. Okay. And what are the things that you have to remember here is that current flowing through each of the resistance will be same, and the potential difference is the sum of the potential differences of the individual resistors. Okay. Now this is a very simple sum. Let's just go over it. So what I told you is that here also, instead of a straight line, here is just given like this, but it is one circuit, right? It's coming to one circuit. So we can simply just add the resistances to find the total resistance. What it is? 20 plus 10 plus 30, which gives us 60 ohm. Don't forget to write the unit. So we know that 60 is the total resistance. We know that the circuit's voltage is 12 volts. So now I think we can find the current, right? So the current is Vs by Rs, which is equals to 12 by 60, 1 by 5, or 0.2 ampere. Okay. Now we come to parallel resistance. So in parallel resistance, if you look at here, what you can observe is that here the potential, like the point of attachment of all the resistance is the same. R1, R2, R3, all of them are connected to X and Y, right? So what does this mean? It means that the potential difference between all these circuits, like all these individual resistors, is the same. So V1 equals to V2 equals to V3. Okay. Now, will the current be same in all these resistances? Like why will it be same? Why will it not be same? I'll tell you, because if you observe here, the I is going. Here it is also I. Now it has to be divided into 3 parts, right? Because it has to supply the current through all these 3 resistances, and it cannot be so that here also I1. If I tell you that all these resistances have I amount of current, then what does it mean? It means that when the current is again passing through, coming out of Y, it will be 3I. Well, that is not possible, right? The circuit's current will always be I. So this you'll learn in class, in the higher classes, that it's the junction law, that obviously the sum of the currents through all the individual wires will be equal to the wire coming out of that junction, right? I input equals to I output. So I1 plus I2 plus I3 will give you total I. So I equals to I1 plus I2 plus I3, right? Okay. So again, if we calculate now, what are we going to find? Is that our main goal is to find the total parallel resistance, or the resistance of the circuit. So again, if we write this time we have to do it a little differently. So Rp equals to Vp by Ip, right? Or V here will be the same, so let's just write it as V. Okay. So V by I equals to, or in an easier way, what we can do is we can directly just replace the currents here. So if we take this equation, only, so what is I? V equals to IR, therefore I equals to V by R, right? So V by Rp, remember, is equals to V by R1 plus V by R2 plus V by R3, right? Just remember this formula, then it will be easier for you. So now we know that we have to take the V common. One by R2 plus 1 by R3. So 1 by Rp equals to 1 by R1 plus 1 by R2 plus 1 by R3. So you can understand from here we get the relation of the parallel resistance. Okay. So now let's show some extra calculations here, but it's not required. Like once you are well aware of how things work, you don't have to remember formulas for everything, but still, since they have given it here, let's just go over it once. So you know that all of their potential differences are the same, right? So V equals to I1 R1, V equals to I2 R2 R3. It's fine. So to find the individual currents, we just have to divide the potential difference by its individual resistances. Okay. So this is simple. You don't have to remember the formula. I'll just come to you when you have practiced enough. Okay. So now heating effect of current. You know that whenever there is there's all like according to the law of conservation of energy, energy is always converted from one form to another, right? So you know that electrical energy is also converted into what light energy. When we see the light bulb, like all the appliances in our houses, they are what basically electrical energy getting converted into different forms of energy, right? So sometimes it does happen that all the electrical energy, it does not convert into totally the other form of energy. For example, if I say that light bulb, okay, so in a light bulb, what is happening, electrical energy is getting converted into light energy, right? But if I tell you that electrical energy was 40 joules, for example, and the light energy or the bulb or the energy required for the bulb to glow was 36 joule. Okay, so where did that extra 4 joule go? Basically, the 4 joule was dissipated in the form of heat. So if you don't try this, but the what happens is that if by chance it has happened to you anytime that if you've tried to fix the light bulb or you've tried to like for by mistake touch a light bulb after it was switched off or switched on, you'll understand that it became really hot, right? So much so that you had to in like you had to immediately like remove your hand. So why does that happen? It because the some of the energy, like some of the electrical energy gets dissipated as heat energy, like not a very huge amount, otherwise the light would have burst, but some amount. So that's why you can feel that heat coming out of that light bulb if you by chance have touched it. Okay, so that is basically the heating effect of current. It is nothing but the dissipation of electrical energy in the form of heat. Okay, but how do we calculate it? So we have certain formulas with us that we have studied up until now. In our work energy power, we had studied how P is equals to work done or energy input per unit time. Okay, let's just not write Q here. Let's just write E here. So P equals to W by T. Okay. Okay. Another thing is that what we know is that potential is the work done to move a charge, right, from one place to another. Okay. So this is formula number 1. This is formula number 2. Right? So now you can understand how we can formulate this here, right? What am I going to do is that, let's just write it fresh for easier understanding. If I substitute the W, then W is V into Q, right? Now I'm substituting this W into this equation. So P equals to Q V by T. So in our first class of current, if you have missed it, you can just go to our YouTube channel and watch it. we knew that Q by T is nothing but current, right? So P equals to IV. So this is one equation that we are getting. Okay, P equals to VI. Achha. So now, if we have to find the energy dissipated, or like the amount of heat, for now we have just found out the power, right? Now we have to find out the amount of heat. Amount of heat means energy, right? So P into T equals to IV into T. Like we have to multiply both the sides by T, then only we'll find the energy. So energy equals to VIT. Okay. Another thing, if V, if the value of V is not given in our equation, so what do? We simply just again use this formula. So E equals to IR into IT, which is nothing but I square RT. Okay. So the energy dissipated in the form of heat is equals to I square RT. This brings us to the Joules law of heating. So the Joules law of heating gives us this formula only, that E equals to I square RT. Okay. So from here what you can understand is that more the amount of current flowing, more will be the heat dissipation. More the resistance, more will be the heat dissipation, and more like the amount of time that you're keeping an electrical appliance on, the more amount of heat will be generated in that appliance. Okay. So now we're gonna like, till now we talked about how it is like a wasteful energy because we don't really do anything with the heat dissipated from a light bulb or a tube light or a computer or a CPU, right? But here there are also some applications too. First, let's talk about the undesirable aspect that we just discussed, how it converts useful electrical energy into heat. In electrical circuits, the unavoidable heating can increase the temperature of components and alter their properties. Yeah, like I told you, sometimes the heat energy may be so much that the bulbs could burst, right? However, the heating effect of electric current has many useful applications. You know, the laundry iron, that is very useful to us, the electrical toaster, electrical oven, electrical kettle, and electrical heater are some of the familiar devices based on Joule's heating. So now you know that how the energy is being calculated here. It is by E equals to I square RT, right? And now you know that how these appliances have their current, have the electrical energy getting converted into heat energy directly. So now here the heat energy is only the main thing, right? So here we get, that's why the amount is so much more, because here the total amount of current through the circuit is being converted into the electrical energy, as opposed to the previous one where it was just the dissipated heat. Okay. So you can understand here that how it is used to produce light. The filament must retain as much of the heat generated as possible so that it gets very hot and emits light. It must not melt as such. So that is why a very unique metal is used for light bulbs, that is tungsten, which is used for making bulb filaments. It can withstand a very, very high amount of heat energy. Another common and very important application of Joule's heating is the fuse, which is used in electric circuits. So I'm sure you're familiar with the term fuse. What it means is that sometimes there can arise a short circuit in your electrical wiring of the house. So for example, so what happens is that sometimes, if I tell you that this is a circuit and this is a bulb and current is flowing, sometimes it so happens that for some weird reason another circuit is formed like this. So what's happening is that the light bulb, which would have um, gotten the energy, like the heat energy or the electrical energy or the current flowing through it, it bypasses the light bulb and all the current starts flowing like this. So this is a short circuit, because before the circuit, like it's not going its original path, it's taking a shortcut. So what happens here is that here at this particular point, there is very increased amount of electric current flowing through it at one particular time. Okay, so what happens is that sometimes this will lead to obviously a problem, right? So like the whole circuit can get disrupted, and you might lose current for a few hours. So what the main thing of the fuse is that they are placed in the electric circuits in such a way. For example, if this is a fuse, so when too much of current is flowing, then you know that by the formula E equals to I square RT, too much of current is flowing means too much of too much of heat energy generated. And what happens is that when too much of heat energy is generated, this fuse melts. So what we get is that we get a open circuit. So I'll just so once this fuse is burnt or this fuse melts, so what we are getting is something like this, right? So this is an open circuit, and open circuit means that there will be no flow of current. So the circuit is saved, and the appliance also most of the time it gets saved, and there is no problem with other appliances also. So the fuse is placed in series with the device. It consists of a piece of wire made of a metal or an alloy of appropriate melting point, such as aluminium, copper, iron, lead, etc. When the time comes, the fuse automatically melts, and then the circuit is broken, and so no amount of extra current is flown through the device, and the device is saved. Okay. This was the concept that was earlier used, like fuse. Now in today's new appliances, another type of fuse is used, and that is basically something that is not made up of a metal in general. It is basically like a switch sort of a thing. So what happens is that the moment the circuit realizes that too much of current is flowing through one particular point, it will automatically switch off, as a result of which the circuit will be broken. And so what we can do is that we go to our respective meter board, and then we again we connect or we mend the circuit, or we just switch it on again, and then the circuit is again completed. So here there is no, like, the only difference is that basically this fuse was very, like, changing it every once in a while was very cumbersome. So scientists came up with a new form of fuse where you just have to switch, like, automatically the fuse will switch off when it detects a very high amount of heat energy, and automatically after some time we can go and we can switch it back on again, and the circuit will be completed again, and the appliance will get switched on again. So that is it. The last part is of this discussion of our class is electrical power. So just now we were discussing about how power equals to power equals to W by T, W equals to VQ, so power equals to VQ by T, or power is equals to VI, right? So another way to define power is that we change this current and we replace it by IR, so I equals to V by R, right? So power can also be written as V square by R, V square divided by R basically. So this is important to us whenever we like have to calculate the power generated by this device without when there is no current given. And also we can understand something, that is the relation, that is more the electrical potential, more will be the current, more will be the power, sorry, and more the resistance of the particular appliance, less will be the power of the appliance. Okay, so that is why this equation is important. And yeah, so this brings us to the end of this discussion, and in the next class we'll be discussing some of the sums related to the current. Thank you for listening.